Our next speaker is Daniel Ollech from the Bundesbank. Seasonality test for weekly and other non-integer seasonal time series. Daniel, are you here?
Yeah, I'm here.
There you are. Okay.
Yeah, exactly.
Thank you.
All right, I'll start sharing my screen. All right. So what I want to do today is discuss two seasonality tests that I try to adapt to take into account or detect seasonality for especially weekly series, but more generally for a series with a non-integer seasonal frequency. So obviously the number of years, the number of weeks per year varies from year to year, and it's a little bit more than 52 weeks a year. And so we traditionally what we would do is we would just ignore the fact and just assume that each year has 52 weeks of observations. But I think we can do better, and I want to show you some results. In fact, what I will present you today is how I think one can go about getting a flexible version of the QS test that Tucker has presented before, and also the F-test on seasonal dummies. Now, I will only briefly go over the QS test because I just want to show you the results and show you that it may work. And then in more detail, I will discuss the F-test on seasonal dummies because there are to me, there's still some open questions, and I'm hoping that some of you in the audience may have ideas on how to go about improving what I've done thus far. So the QS test is basically a test on seasonal autocorrelation. So the part that is interesting here now is the autocorrelation part. And in contrast to, say, a monthly series where we compute the autocorrelation for the observation today with what we had 12 months ago for weeks, the seasonal signal that we see today relates back to something that we saw 52 weeks ago and 53 weeks ago. So because we have 52 point a little bit weeks a year, the seasonal signal more or less moves a little bit from year to year. So what we straightforwardly can do then is we can just combine the observations in week 52 and week 53 and use that to compute the correlations. So the unobservable observation in T minus tau, where tau is the seasonal frequency here for weekly series, for example, 52.14 or 18, can be a combination of the observation in YT minus the floor of tau, so 52, and YT minus the ceiling of tau, so 53, and using some weight alpha. What we have to keep in mind, though, is that the observation, for example, in T minus 52 contains the seasonal signal YT minus tau, but also basically includes some noise, if you like. So something unrelated to the seasonal signal. And alpha is just given basically by the share of if you think about days in a week, then there will be some overlap of 6 out of 7 days from the current week to the week 52 weeks ahead. So this is basically designed to capture the seasonal signal and the weight of the seasonal signal. And so we can just use this Y star naively, but in fact, because as I said, there is we can basically combine something seasonal with something that we can consider noise. We have to come up with an attenuation factor because the correlation will be mitigated, that is biased towards 0, and this attenuation factor will counter that. I'll show you some results that this is a good idea in a second. The proof I will put in a paper. This is too much for today, but this is the attenuation factor. The squares and so on come from variance assumptions. All right. So here we have the QS test, how it behaves under the null. So we assume that the QS test follows a chi-squared distribution with 2 degrees of freedom. And if we have a frequency of 7, so a integer type seasonality, it is very close indeed to a chi-squared distribution, as we can see here. Or if you look at the p-values, it's very close to a uniform distribution. If we use the flexible version of the QS test without the attenuation factor for now a frequency of 6.5, so a non-integer frequency, you can see there's a strong bias. Now here in the p-values, it no longer follows a uniform distribution. The same here is no longer follows the red line, a chi-squared distribution. And with the attenuation factor, we get very close to uniform distribution of the p-values or the chi-squared distribution of the test statistic. So showing that with the attenuation factor, the null distribution still works, and indicates that it's a sensible attenuation factor indeed. Just briefly, some preliminary simulation results comparing what we would get if we would just ignore the non-integer nature of the series and contrasting it with if we use the correct flexible version of the QS test or the adapted QS test. And so just some integer, non-integer frequencies that we're looking at. So 52.14 is 365 divided by 7, so a weekly series, a 2-weekly series, an 8-weekly series. And so if we have had 3.5 days per week and so on. Anyways, what we see is with the traditional QS test, so if we ignore the non-integer nature, we have very low detection rates of seasonal series, especially for the series with naturally fewer observations. The difference becomes smaller and smaller the longer the frequency and the more observations we get. Here are size estimations for non-seasonal series or the rejection rate. So basically, the lower number, the better. And we see even for weekly series, we get a slight improvement in the sense that non-seasonal series are not classified as seasonal. So it's better with the flexible version. All right. All right. And now to the main part, basically the tradition or the flexibilization of the F-test on seasonal dummies. So in a Regarima model, given here, we can put in some regressors that capture stable seasonality. Usually this is done using seasonal dummies. And the test statistics is then given by this thing. But the important thing is now the betas and the variance covariance matrix. So basically the standard errors and the coefficients. And the rest is some degree of freedom stuff. So when we adapt the seasonal dummy test, again, we have to keep in mind that what the seasonal observation today relates back to something that we had 52 and 53 weeks ago, and then 104 and 105 weeks ago. And so by constructing regressors, again, that combine these observations, we can try to track the seasonal signal better than we would with seasonal dummies. Yeah, so it's basically combinations of neighboring observations of the regressor, and then the weight given by the distance of the observation of the seasonal signal to the observable observations, if you like. So just briefly, an example for a seasonal frequency of 2 1/3 would look like this: a 1 in the current observation, then nothing in the t-1. So, and then in t-2, which is quite close to 1/3, get a weight of 2/3. And then with the 3, we have a weight of 1/3 and the t-3 observation. And this is basically just a lag of the first one. An alternative, and maybe a more common or maybe a more straightforward alternative indeed, is to use trigonometric regressors. So combinations of sine and cosine terms, which for integer seasonal series indeed are equivalent to the seasonal dummy variant if you have the same number of regressors. So in each case, again, the test statistics is given by this guy, where the part that interests us the most is the beta and the betas and the variance matrix. And from measurement error theory, we can assume, or we may assume, that the betas probably are unbiased, but the variance covariance matrix may be biased. And one solution then is to bootstrap the variance covariance matrix. Here, this is a sieve-type bootstrapping algorithm that I devised and adapted from the bootstrapping of ARIMA models for prediction intervals. I'll leave that as a reference, but just I'm going to skip it due to time concerns here. And instead, I'll show you some results. So how much is the null distribution distorted for the standard seasonal dummy test? So what we see here is for a frequency equal to 7, that is, we just use 7 seasonal dummies or 6 seasonal dummies in a constant term. P-values are uniformly distributed. The f-test works quite well. Now, without any adaptation, but using the flexible seasonal dummy test, we see that, again, a frequency of 6.52 in 8 weekly series. There's some, the null distribution is distorted or biased somewhat, which we also can see here. And interestingly enough, the same case, this is also the case for trigonometric regressors without any adaptation. And so I was searching in the literature trying to understand why this is happening, because I don't see why it should happen. And I couldn't find anything. So anyone can point me to any references, I'd be very happy to read about that. So what we can do, obviously, is bootstrapping, and I'll show you the results in a second. But what we can do also is just simulate the null distribution and use that for our test statistic. And of course, if we simulate the null distribution works quite all right in a straightforward manner. Now, with bootstrapping, it's not perfect, and indeed, my results show it depends on the sample size, which is not very elegant, but it's at least an improvement compared to doing nothing. But it takes a lot of time, because obviously with bootstrapping, here we have a sample of 2000 or resampling of 1000, I mean. You have to calculate 1000 ARIMA models, and this can take a lot of time, especially for longer series. So for weekly series, it takes a long time. So taken together, the null distributions are biased, and I suspect it's because the variance covariance matrix is biased due to the construction of the regressors, and that we combine observations. But I'm not sure why this is also the case for trigonometric regressors. So simulating the null distribution helps, and some preliminary simulation results for just detecting seasonality shows that it may be a good alternative. Bootstrapping the null distribution, not the null distribution, bootstrapping the variance covariance matrix also helps, at least somewhat, but it's far from being perfect. So my open question is, why exactly does the test statistics need to be adapted? And even for trigonometric regresses, question is it a small sample problem? So maybe we don't need to do anything for weekly series at least. And then how maybe best to adapt the test statistic? So is it necessary to adapt the test statistics, or can we just assume it's a small sample problem, which at least for weekly series isn't a matter of concern? And that's all these questions I will try to answer in future research. Right, so summing up, so I have some ideas how to generalize the F-test on seasonal dummies to non-integer seasonal time series. I showed how to implement a bootstrap, and the results are promising from some simulation studies I started, but there are yet some open questions. All right, and here's some references. All right, that was it.
Thank you. All right, so we have a few minutes again for questions, just a few. But if you have any questions for Daniel or for the other speakers, again, please type them in the chat. Or if, yeah. Okay, so we are nearing the end of this section. Oh, sorry, we have a question from Tucker. Tucker wanted to ask Daniel, have you looked at spectral tests?
Not yet. Yeah, basically, because I was starting out with what we have in JDemetra and thinking about how we can go about flexibilizing these tests. And with spectral tests, there are a lot of, I feel, ad hoc measures for how to combine, like the, what is it, the, because there are two spectral tests that are combined in what we have in JDemetra, and there's some assumption on how to combine them, and I feel like it's not straightforward how these should be combined, or what should be the criteria for weekly series. So I didn't even start on that because we thought about that when we looked at daily series, because for daily data, just looking at a spectrum is very helpful in just detecting visually seasonality, but it's not as straightforward to have a formal rule on for something like a statistical test. So that's why I haven't done it yet.
Okay. Again, we have a little bit of time left, but just to remind everyone that this room will stay open for our next set of talks, special topics in seasonal adjustment and modeling. Those will begin at 45 minutes after the hour. And if you want to attend the breakout section, the lightning session. I called it the lightning round. Brian told me that was incorrect. You can see the link. Brian posted it there for the lightning sessions, which will also begin at 45 minutes after the hour. All right, I don't see any other questions right now. So we will go ahead. You can still submit questions on the chat. This room will stay open. Thank you, Tucker. This room will stay open and we will reconvene at 45 minutes after the hour. Thank you.